Assalamu alaikum. I would like to talk about design of experiments today, focusing on a statistical approach called Way ANOVA. DOE is an acronym for Design of Experiments, which is not actually focusing only on design procedures, but also it includes analysis. An experiment has some controllable input X, which is processed to obtain an output Y using measurement techniques. We perform DOE to improve the efficiency of a process or a product, as well as experiments are performed for validation purposes, especially when you are about to launch a product to the market. An experiment is a procedure in which we check the effect of some input variables on the output. Also, it is used to illustrate a known effect or to test a hypothesis. Let's say if we want to check the efficiency of a cake making process. We have various factors that affect the cake characteristics. To make our cake the best, we have to check its taste, color, consistency by optimal selection of temperature of the oven and the amount of ingredients. These factors can be quantified with different levels. For example, the oven temperature is one of the factors that has an effect on the consistency of the cake. We can check by setting different temperatures such as 150, 200 or 250 degrees centigrade. Another example, let's say if we are experimenting to improve the strength of a material by changing the temperature and pressure. We can set 3 levels of temperature at 100, 200 and 300 degree centigrade, while 4 levels of pressure at 5, 10, 15 and 20 pounds per square inch. These two factors are input variables that are independent, that affect the response of the experiment termed as output or dependent variable. We check if the temperature or pressure have an significant effect on the strength, which means if changing these factors, the output changes, otherwise the factor is insignificant. If the output is not changing. Specifically, ANOVA is all about checking the significance or insignificance of a factor. Or if there are two or more factors, we also determine the interaction of these factors. ANOVA is an acronym for Analysis of Variance, which is a statistical procedure used to test the experiment if the factors and their interactions are significant or not. Like sampling distribution, but we have two or more groups whose variances are compared. So far, we have known that a factor is quantified which can cause variation in the response, and these factors may have a finite number of levels, just like we discussed the effect of temperature and pressure on strength previously. We always perform experiments by putting some input variable with different values. We classified it into groups called levels and we get the response. This response can also be replicated. The next step after determining the input and output variables, hypotheses are defined, similar to the sampling distribution. With two or more groups, we first assume that the population means are equal. That is, there is no effect of factor on the response. It is only possible when there is no variation between the groups. This is the null hypothesis. On the other side, we test with an alternative hypothesis in which factor effect is considered, meaning that not all of the population means are the same. Variation in response due to different levels of a factor can lead to significance of that factor. We can say that starting with null hypothesis, we assume those factors are insignificant and then perform the analysis to make a decision. If there is a variability between groups, or to say between levels of the factor, and the variability is found, the factor is significant. Within group variance, usually called error variance, refers to the deviations caused by differences within individual groups or samples. Each group is considered independently. No interaction between them is involved. Between group variance is found quantifying the spread of the sample means. F-test is followed for the analysis of variances, and F-value is formulated by dividing between group variance by within group variance. Between group variance is also called factor variance. These variances are calculated by taking sum of squares of the deviations. Between group variance is large relatively to the within group variance, so that at least one of the group means is significantly different from other group means. Between group variance is also termed for factor and within group for error. If the within group variance becomes large compared to the variability between means, that is the between group variance, the groups are very close to each other. That makes group means equal. Looking at an example of one-way ANOVA in which there is only one factor involved but with multiple levels and replicates. These replicates are the exact copy of the input variable at a certain level. For example, the cotton weight percentage is a factor that is tested if it has any effect on the tensile strength by changing the levels. Here there are 5 levels that are 15, 20, 25, 30, and 35 percentages of cotton weight. At 15%, the first output of 7 pound per square inches is obtained, and keeping the same percentage, this is replicated 4 more times. Similarly, this is performed for other 4 levels, making a total of 25 observations. The output variable is a dependent variable represented by a symbol y, having 2 letters in the subscript I and j. I relates the level and j relates the replicate. At first level and the first replicate, the output is y11. The same level but second replicate y12. Similarly, y13, y14, and y15. At the second level, the first replicate gives y21, and this goes on. The total of the observations of replicates at level 1 can be written as y1 dot, while the average includes a bar over it. The overall average can be written as y bar subscript y dot dot. If we take the grand sum, we can write it as y dot dot. The deviations cannot be summed up to form the variance. Rather, the sum will be 0. So we sum the squares of deviation between a certain level mean and overall mean. By dividing this sum of squares by degree of freedom n-1, we can obtain variance, which is also known as mean square. The sum of squares of factor deviation is found by this approach. While for the sum of squares of error or within group, we find the deviation between each observation and its certain level mean, which could be y1 dot bar, y2 dot bar, and so on. The total variance SS total can be found by finding deviation between each observation and the overall mean, or other way equating SS total to the sum of SS factor and SS error. We can then find our mean square, which is the variance, by dividing it by degree of freedom of the respective sources. Then we can find our F value by dividing the mean square of factor by mean square of error. Now going back to the example, here we have 5 number of levels, which is represented by A, small n for the replicate. Here number of replicates are 5, and total number of observation can be found by multiplying number of levels with number of replicates. It comes to be 25. Now using the formula of sum of squares, we have SS of factor equals to the sum of the squares of deviation between the mean at a certain level and overall mean. Here we can write it as n times the summation. Now substituting the values, we can solve it and find the SS of factor. Here we get SS of factor as 475.76. Now finding sum of squares of total observation. We know the formula that it is the sum of squares of deviation between each observation and overall mean, while SS of error is the sum of squares of deviation between each observation and average at a certain level. So first we will find the SS total, and we have to find each and every deviation by subtracting with overall mean. We get the value of SS total as 636.96. Now finding SS error, but we won't use this formula. Rather, we will use the formula of SS total, which is equal to sum of SS factor and SS error. So SS error can be found by differencing SS total and SS factor. So by putting the values, we get SS error as 161.2. Moving forward, we will find degree of freedom, mean squares, and F value. So degree of freedom of factor is the number of factor minus 1. And also we know that number of observations are capital N, which can be subtracted by 1. And for error, we have the formula, or we can subtract total number of observations by number of factor. Here we get degree of freedom of factor 4 by subtracting 5 by 1. We get the total as 24, and the degree of freedom of error is 20. The mean squares can be found by dividing sum of squares by degree of freedom. Finally, we can get the F value by dividing mean squares of factor by mean square of error, and it is found to be 14.76. So after getting the F value, we have to formulate the hypothesis. First, we have to go with the null hypothesis, that is, the factor is insignificant. On the other side, an alternative hypothesis can be set, which is the factor is significant. So we will set the rejection zone and the acceptance zone. The rejection region lies at the upper tail with a confidence level of 95%. Here we will find F alpha, which is the critical value of F, and here nu represents the degree of freedom. Nu1 is the degree of freedom of numerator, which is of the factor, and nu2 is the degree of freedom of error, which is at the denominator. Alpha is also termed as level of significance, which is 5%. If we subtract it by 1, we can get the confidence interval, which is also known as confidence level. So the upper tail has the shaded region, which is the rejection region, and the unshaded region is the acceptance region. So if our value of F lies in the rejection region, it means that the null hypothesis is wrong, and we can take the factor as significant. So now taking alpha as 5%, which is 0.05, degree of freedom of factor nu1 equals to 4, and degree of freedom of error 20. From the chart of F value with alpha 0.05, we can find the value of F critical. So here it is found to be 2.87. However, F naught is 14.76, which means that it lies in rejection region. So our null hypothesis is failed. So we will reject the null hypothesis and conclude that the the factor is significant. It must be understood that the objective of ANOVA is to check whether there is inequality of means, which implies that we are concerned with large variations between samples as compared with variations within samples. When the variations between samples is small, resulting in f value being on the left side, it doesn't matter as this difference is significant. The variations between sample matters if it is significantly higher than the within variations, and in such case the f value would be greater than 1. Therefore, in the right or upper tail, the rejection happens only when the f ratio is on the right side, and never when on the left side if f0 is less than 1 or around 1, which indicates to the lower tail. This means mean square of factor is very small and not much variation happens, and this leads to rejection, which is not possible to conclude the significance. P-value is the probability of getting a result at least as extreme as the one that was actually observed, given that the null hypothesis is true. The p-value is the evidence against a null hypothesis. The smaller the p-value, the stronger the evidence that you should reject the null hypothesis. P-value less than alpha lies in rejection region, while p-value greater than alpha lies in acceptance region. So a significance level of 0.05 indicates a 5% risk of concluding that a difference exists when there is no actual difference. If the p-value is less than or equal to the significance level, you reject the null hypothesis and conclude that not all of population means are equal. One way ANOVA model can be expressed in mathematical form as Yij equals to mu plus tau I. Here Yij is the individual observation or the variation in response. Mu is overall mean and tau I is the effect of ith level of factor. It is actually a fluctuating component, or to say a residual. If we subtract the individual observation with the overall mean, we can obtain different residuals at different levels. This equation can also be expressed as for every individual observation is equal to the mean value plus fluctuating component. We can express this in a straight line form where y is our output, and with different observations with different levels of factor we can obtain a slope, while the y-intercept represents the overall mean. It is similar to the regression model, which is a technique to fit a straight line through the data points. It models the quantitative relationship between two variables, x and y, and it is quite simple because only one predictor variable is involved. It is called simple linear regression. It describes how one variable changes according to the change of another variable. Both variables need to be continuous. There are other types of regression to model discrete data. So for example, if we have these data points with different levels of a factor, for example, there are 5 levels and we have found the means of each level. Here we can fit a line in between these data points and find out each of the fluctuating component. We can find fluctuating component by taking a difference between average at a certain level and overall mean. So for the first level, we have the values 9.8 and the overall mean is 15.04. If we subtract them, we get a negative value of the fluctuating component. Similarly, we can perform for the next levels, and we can see clearly that some of the responses have positive fluctuating value and some have negative. These fluctuating components can also be termed as residual, which is equal to the difference of observed value and fitted value. Observed value is measured and it is taken from the experiment, while the fitted value is calculated from the model equation. It is also called predicted value. If we subtract the observed value and fitted value, we can find each residual, which is represented by E. And if we want to get the variation, we can use the method of least squares. And for this, we sum the squares of deviation. How to get these data set fit for a model? We try to make that curve or a model to pass through the maximum number of data points, and we find which equation is the best fit. It may be linear, quadratic, or other types of model. We can use equation of straight line or quadratic equations or cubic equations or even exponential equations. If we consider that this equation of a straight line is the best fit of our model, we can get the predicted values in between. For example, y equals to 3 plus 4x. Here 4 represent the slope and 3 represent the y-intercept. If all these data points are on this line or curve, then we say that our observed value is equal to fitted value. But if there are data points different from fitted value, the difference is called residual. So some residuals must be positive and some negative to fit the model adequately to make the model reliable. But if our fitted model has data set above, then the model is said to be underestimating the response, which means that all the residuals are positive if we get the observed value greater than the fitted value. Similarly, if we have the data set below the fitted curve, then the residual is negative and the model is overestimating the response. So not all the data set should be above the fitted value or below the fitted value. It should be in between. Also, we try to make our outliers as minimum as possible. So our data point should not be that far away. If we have that data point far away from the fitted value and all the data sets are near to the fitted value, only one or two data points are far away, we termed them as outliers. So there should be minimum outliers or zero. Also, we have model adequacy check in which we check how the residuals are arranged. There are three conditions of the model adequacy check in which we check that residuals have a constant variance and they are normally distributed, and also they are independent of each other. To check the model adequacy, the first condition is all the residuals should be normally distributed, which means that all the residuals must be arranged with a constant mean value. So the data points should be near to the overall mean in order to make the data points normally distributed. It can be checked with the coefficient of determination, which will be discussed later on, termed as R square, which provide the goodness of the fit. Here we can clearly see that the data points are near to that regression model or the model equation line. Similarly, we can see the histogram where the mean values of residuals should be zero. That is, the mean lies at the center of this curve. In second condition, we check if the plot of residuals have a divergent funnel or nozzle shape. This means that variability in the response is changing as the predicted value increases. So, residuals should not have variable variance, rather it should have a constant variance. We term this separation of residual as heteroskedasticity. We should not have that condition in which residuals are separated and form a divergent funnel or nozzle shape. We say that fitted values should be close to the observed values and there are no variation in the residuals. So this is how we check the second condition. For the third condition, we check the order or the period in time intervals or arrangement. So there should not be a sequence followed. The residuals should be independent. There should not be autocorrelation. The errors which are modeled with respect to different periods should not be correlated. So in order to check this, we should make our experimental values completely random. So the third condition is checked if the values are independent to each other. For example, we have pressure buildup in a line. So the values checked with the arrangement of time should have dependent values. Or we check the solar radiation data because the subsequent observations are dependent upon previous observation. This is also not adequate. Furthermore, if we are checking the temperatures of a boiler when it is starting up, the thermal expansion is on rise, temperature is on rise, so we cannot do the experimental work at that moment. So the data set should be completely random with respect to their order. There should not be dependency on the previous data. So if these three conditions are not being followed, there is no reliability of ANOVA, and we cannot say that if the factors that we are focusing on are significant. Previously, I talked about the fitness of a model, and it is determined by checking coefficient of determination. For our ANOVA model, we can find R square equals to 1 minus the ratio of SS error and SS total. Also, if we divide SS factor with the SS total, we can find the coefficient of determination, and it tells us about the percentage of how the model fits, how the data set is close to that fitted model. If it is 100%, then the model is consistent and it is termed as very good. We consider R square values greater than or equal to 80% for curve fitting. 80% of the coefficient of determination is termed as good, but below that is not good, is somehow average till 40%. 40% and less than that is not a good fit. However, if it is close to 0%, we perform the experiment again with different technique and strategy. These residual plots can be obtained from statistical software such as Minitab or SPSS very easily, and we can predict our model. We can tell that if our model is adequate, and we can proceed on with this experiment. For example, the cotton weight percentage effect on this strength. Here we have the R square value of 71.92%, which is quite okay. Not that good, but that's an average for accepting the model. Here we have the residuals in the first figure normally distributed, which is near to the curve, and also the histogram tells us that it forms the bell shape. In the second figure, there is no divergence or convergence, so we have constant variance. Also in the last figure, the order is completely random, so we don't have any dependency. So we can say that our model is adequate, and also the closeness of the fit is fair enough. So that's all about Way ANOVA. Thank you for listening. Allah Hafiz.